I'll get my screen shared here. Okay, everybody seeing the presentation okay? Great. All right, so yeah, I'm going to talk today about brain-computer interface, or BCI, as an AAC access method. So I'll tell you a little bit about myself. I guess Carolyn already just did that, but I am a research assistant professor at Oregon Health and Science University and part of, we call it CAMBI, the Consortium for Accessible Multimodal Brain-Body Interfaces. I'll talk a little bit more in just a moment about what that is and who else is part of that group. In the past, I've done some clinical work for the local chapter of the ALS Association, as well as working as an AAC specialist at the Portland VA. That was mostly with veterans with ALS. So that's my primary clinical background, working with folks with ALS, helping them with AAC, and also with assistive technology for accessing the computer and telephone and things like that. I still do a little clinical work with people who are undergoing awake craniotomy. Most of my AAC related work these days is research, and primarily in the field of brain-computer interfaces. I've been doing research on BCI for about 10 years now. So a little bit more about CAMBI. We are an interdisciplinary team with sites across the country. So here in Portland at Oregon Health and Science University, we have our clinical team that's led by Dr. Melanie Free-Oken, another speech language pathologist and assistive technology specialist. We have worked with other SLPs on our team over the years, an occupational therapist who specializes in vision impairment. And our role is really to represent the interests of potential BCI users and to help design experiments for testing our systems and new features with people with disabilities and to bring our clinical expertise. We also work with a signal acquisition team that includes a neurologist and specialists in EEG data acquisition. Our development team is based at OHSU, who do all of our software, our coding for our programs. And we bring in potential BCI users. So people with severe disabilities, we want them involved at all stages of the research process. We want them to be, helping to inform our designs. We want them to be helping to think about what experimental questions we want to ask. We want them to be testing things and giving feedback. And we try to value their participation and provide them with some compensation. So they're a really important part of our team as well. At Northeastern University, we work with the electrical and computer engineering department, and they do a lot of the fancy math that goes into our BCI, which I'm really glad there are other people to do that stuff because it's well over my head. We have a language modeling team at Michigan Tech, and we have an experimental design specialist at the University of Washington. So I'm going to talk a little bit more later about some of the BCI systems that we have developed as part of our research, but just wanted to give you a little bit more of a background about the team that I work on. So on the agenda today, I'm going to talk about how BCI works as an AAC access method. We'll look at some of the hardware that's involved, talk about some of the different brain signals that can be used for control and what users are asked to do in order to produce those brain signals. And we'll watch some video demonstrations of a few BCI typing systems so you can get an idea of how these things actually work. We'll talk about who are the potential users of BCI, some of the practical issues associated with eventual clinical implementation of these systems, and we'll end with a case study. Nobody submitted a case study for today, so I did come up with one, but if you're going along through this and kind of thinking, I wonder if somebody I know, or I can imagine someone similar to people I've met who might benefit from BCI, and you want to bring that up at the end, please feel free to do so. So I want to start with a little poll. I'm curious about what people know about BCI these days. It is more in the news. There have been some articles in, things like the ASHA Leader and other publications. So I'm just kind of curious, what do you know about BCI? What's your level of familiarity with it as an AAC access method? And while people are are filling out the poll, I'll just also mention, as Carolyn said, please ask questions and feel free to do so during the presentation. Type them into the chat. I'll also pause kind of at section breaks and ask if people have questions. Feel free to either type something in the chat, or during that time, if you want to just unmute yourself and ask a question, please feel free to do that as well. Okay. So do we have the poll results? How do we see those?
They're still coming in. I can tell you at the moment, we've got somebody here has worked with people. We have.
I think that was me.
Oh,
I took the poll too.
That would make sense. I was shocked. 27% have read articles or watched videos. 36% have heard that it could be used for AAC access but don't know how it works, and 27% so far have gone with what the heck is BCI. Okay.
Okay, so pretty even split. Some people know some things and some people are coming to this fresh, so that's great. I'll try to kind of tailor things to people with different levels of background knowledge, and again, please do ask questions as we go here. All right, so let's do a quick introduction to BCI. A lot of you, most of you probably are familiar with some of the more traditional access methods that are out there. If you have the ability to move your hands, you can use a touch screen, a mouse, a joystick. If you can move your eyes, you can use eye tracking. You might be able to use head movement with a head mouse, or maybe you can touch a switch with your foot, or maybe you can twitch your eyebrow. So there are just so many different access methods out there, but really they all require movement of some kind, voluntary movement, even if it's just a tiny, tiny movement, but you do have to have that muscle control. So what do you do if you don't have that movement? If your brain, your thoughts are really the only thing that you can consciously control, what do you do? How do you access a computer? How do you access AAC? So this is where BCI comes in. BCI involves controlling the computer without muscle activity, and it helps people interact with the environment using only their brain signals. Has a lot of possible applications for people with disabilities. Communication has been the primary one in research, but people have also looked at computer access for things like email and browsing the internet, control of power wheelchairs and robotic arms, things like that, as well as environmental controls. And there are also a lot of groups that are looking at the applications of BCI to people without disabilities. So not to replace lost function, but to enhance existing function. But today we're going to focus on applications of BCI for communication for people with severe speech and physical impairments. So how do we get from a person formulating a message in their brain, they've decided they want to say the word hello, how do we get to actually them being able to produce that message, to type it on a screen or to have it produced in synthesized speech? What goes on in the middle there? BCI is often presented in the media as mind reading. I can't tell you how many headlines I've seen related to BCI, some new BCI development where they call it a mind reading machine, or it translates thoughts into speech. BCI is not a mind reading machine. That's not how it works, and it's very irritating to a lot of us in BCI research that it's referred to that way. It can kind of change people's expectations about BCI in both good ways and bad ways. They might expect it's kind of a magic bullet. It's going to help people communicate with no trouble at all. They'll just be able to think, and it will speak for them quickly. That's not how it works. And then on the other end of the spectrum, people are worried about their own private thoughts being broadcast to the world without them intending to do so. And mind reading, are people going to be able to access my thoughts and use that against me in some way, or use it for advertising or things like that? So for both the good and the bad, that's not how it works. BCI does not read your mind. It really acts more like an access method in the way that we're used to thinking about access methods. It gives a control signal to an application on a computer that allows you to produce a message with that application. So there's just really some additional steps in the middle there from thought to producing a message. There are two broad categories of BCI that we're going to talk about today. Non-invasive, you can see my dad there on the left modeling our EEG cap and looking at one of our research systems. And on the right is an image of an implantable BCI. So that's a BCI that requires surgery, and there are electrodes either implanted within the brain or on the surface of the brain. I'm going to talk about how each of these works and give some examples of the different types of systems in these categories. Any questions before I move on about kind of this introduction to BCI? Okay. So let's talk about non-invasive AAC BCIs. There are a few different ways that we can acquire the brain signals, get the data that we use to control non-invasive BCIs. By far the most common is electroencephalography, or EEG. That's the one I'm going to be talking about today. You can also get that brain data from fMRI, or functional near infrared spectroscopy, FNIRS, or magnetoencephalography. All of those last three involve very, very expensive and very, very large, not portable, fancy machinery. So if you're doing it at all, you're going to be doing it in a hospital, probably at great cost, however much they charge per hour, to use the fMRI. They also have those three pretty poor temporal resolutions. So they do show changes in brain activity, either based on the intention of the person or based on a response to stimulation, but those changes occur pretty slowly in the imaging. So EEG has the advantage of being relatively inexpensive, although it is still pretty expensive. We'll talk about that a little bit later. It is portable, it's relatively easy to set up, and it shows changes in brain activity pretty quickly. So that's what we're going to be talking about, a few different EEG typing systems. So with EEG, we have electrodes that are placed on the scalp. They record electrical activity in the brain cells. But they have to do so through a few different layers of things getting in the way. So they're sitting oftentimes on top of hair, and there's kind of some air, some space around the hair in between the electrode and the scalp. Then they have to go through the scalp. Then they have to go through the skull. So there are several different layers in between the electrode and the brain signal. And that causes a pretty poor signal to noise ratio, meaning that the brain signals that we're looking for as a control signal for the computer can be obscured by other things, little electrical activity from the skin, or the movement of the cap against the scalp, things like that. So that's kind of one of the disadvantages of EEG. But this is the same type of EEG that's used for things like sleep studies or epilepsy monitoring, things like that. So pretty standard EEG technology. There are a couple of different types of electrodes used with EEG. This is an old photo of me with much shorter hair applying the EEG cap to one of our study participants. And you can see on the right there, those electrodes are sort of cup-shaped. There's a hole that you can access the inside of the electrode, and then there's a little opening under there. And so it kind of looks like I'm injecting something into this guy's brain. That is not what's happening. That syringe has a very blunt tip, and I'm using that blunt tip to gently abrade the scalp, to brush away any dead skin cells, to kind of push the hair aside. And then I'm injecting some conductive gel into that hole in the electrode to fill in the space between the electrode and the scalp, to make sure that it has a good connection. There are also dry electrode caps. This one is being modeled by one of our team members, Greg. You can see on the left there, there is a band across his forehead. There are electrodes across that band. And then there's this cap that has kind of some spring-loaded little arms that hold additional electrodes against his head that you can see there on the right. There's a picture of the electrodes at the bottom. You can see it has those little metal pins. And the idea there is that they kind of work their way through the hair to make direct contact with the scalp. So you can kind of rotate those electrodes with a little tool from the outside that kind of works it through the hair. And I know that bottom picture looks like some kind of torture device, but it really is pretty comfortable. You know, the cap is spring loaded. It has cushioning. They try to make it snug, but not tight, so it's not pressing those little spikes into your head. Some people do experience some mild headache or other discomfort with it. Some people have no problem at all wearing this cap. And usually even for the people who have some discomfort, we can kind of tweak it and adjust it a little bit to make it work for them. So if you think about, you know, the advantages of wet versus dry, wet tends to have better signal quality because that gel helps the electrodes have a really good connection to the scalp and helps transmit those signals. But you end up with gel in your hair. And if you're a person with severe disabilities, you are most likely not getting your hair washed every day. And you can get some of the gel out with a damp washcloth, but you really can't get all of it out. And, you know, it's kind of gross. It builds up in there. So the dry electrodes don't have that problem, but they are a little bit more prone to causing discomfort, and the signal quality isn't quite as good. So kind of some trade-offs there. When we're using EEG for computer control or for AAC access, there are a few different signal types that are pretty commonly used, and I'm going to talk about 3 of them: the P300 event-related potential, the steady state visual evoked potential or SSVEP, and motor imagery. So the P300 event-related potential is a response to an infrequent or novel stimulus. P stands for positive, and the 300 refers to 300 milliseconds. So it is kind of a spike in the brain signal that occurs about 300 milliseconds, a positive spike about 300 milliseconds after a novel stimulus. So if I'm showing you a series of images and you see potato, 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 parakeet, you will have this involuntary P300 response when you see the parakeet, because it's kind of something new to your brain, and your brain goes, oh, what's that? Without you really thinking about it. And it ends up looking something like this. The red line represents an average response to non-attended or kind of consistent stimuli like the potato. And when there's something new or something that a person is attending to, it produces this little spike in the brain signal. And if a computer has been trained to recognize a person's individual brain responses, so if the computer has seen a number of examples of both, wow, that's the thing I'm interested in, and no, don't care about that, it can learn to differentiate between those 2 responses for that individual. So we can use that for typing by asking a person to attend to the letter they want to type in a stream of letters that's being presented to them. So it's kind of like, don't care about that letter, not the M, not the P, not the Q. Ooh, there's the A. Since they're looking for the A, when they see it, they'll have that P300 response. So we have designed a typing system called the RSVP Keyboard that uses this P300 event-related potential. So developed by the CAMBI team with input from our research team members with disabilities. And I'm going to show you what it looks like. So this is set up as for our copy spelling tasks that we use to evaluate performance in our experiments. We have a target phrase at the top with a word missing that is your goal to copy. So the next letter in that word is S. You're going to be looking for the S. When I click to the next slide, you'll see a red fixation cross in the middle of the screen, and that's kind of telling you to get ready and to look at this point in the screen. And then you'll see a stream of letters that are flashing quickly. I want you to just keep your eyes peeled for the S. So here we go. Okay, so if you saw the S, you had a P300. Congratulations. I'm sure, you know, didn't feel like anything to you, but if you're hooked up to EEG, we can pick that up. And this kind of simplifies the process a little bit. It shows that the S has been selected. Because, as I was saying earlier, the EEG has a pretty poor signal to noise ratio, it can't always get clear information from one stream of letters to know, oh, this person definitely wanted the S. it might get like, oh, okay, I think they wanted the S, but they also kind of reacted to the P or some other letter. And so it might show a couple of different streams of letters, kind of repeating the question, like, did you want the S? Did you want the S? And if you react to it a couple times in a row, that'll give the computer enough information to type something. Maybe I'll pause here for questions before I go on to the next system. It looks like something has happened in the chat. Do we have any questions?
There's a question, Dr. Betts, about the availability of the slides after the presentation.
Oh, okay, okay,
yeah.
Cool. All right.
Sorry, very quick question, Dr. Betts. Is that, or Dr. Peters, excuse me, is that the speed in which you would present the letters to the people that you're working with?
That's a typical speed. That is something that's adjustable, so we can slow it down. And a lot of people, when you present them that quickly, their immediate reaction is, whoa, I can't keep up with that. That is way too fast. I felt like I wasn't able to react in time. But because that P300 is involuntary, it's actually happening without you really realizing that it's happening. So sometimes we'll slow it down. Some people are more comfortable with that. Often, once they're more comfortable, we'll speed it back up again, just because it makes communication a little bit faster, and most people like the faster speed once they're kind of used to the idea of how it works.
Got it. And while you're talking, we got the question, do you present the letters in a hierarchy of frequency?
Yeah, good question. So I mentioned at the beginning, we have a language modeling team that works with us. So the language model is integrated with our system, and it actually selects the most likely letters based on frequency, after the string that's already been typed, what are the next most likely letters? And it'll show kind of the top 10. If the person does not have a strong EEG response to one of those letters, it'll add some new letters and kind of repeat that again. So yes, the presentation of the letters is informed by a language model to kind of support faster and hopefully easier typing.
Interesting. We also had a comment, I'm a little confused about the response. What exactly does a P300 response look like in the brain or to someone else?
Yeah, so let's see. So it looks kind of like this on average. If you're just sitting there watching an EEG stream, which, I'm sorry, my dog decided to be a problem right now. Excuse me. So if you're just watching the EEG stream, which looks like kind of a row of fuzzy lines, one for each of the electrodes, you can't see a P300 in real time. The lines are going to be kind of constantly going up and down. You can't be watching it and see, ooh, there's a P300. But the computer can average the responses and knows what that looks like. So really, it won't look like anything to you. There's no, change in physical appearance. There's no obvious change in the EEG signals if you're just watching somebody use it. It won't feel like anything to the user because, again, it's just kind of an involuntary, like, ooh, there's the thing I wanted. Yeah, hopefully that answers the question. It doesn't look like much, really, except to the computer that has been trained to look for it.
She said yes and thank you. And then we were asked, is there a program for non-literate individuals? Yes. For example, photo or symbol-based responses.
Okay, yeah. So there has been some investigation of using icons instead of letters. We've done that a little bit in our group as well. We can kind of plug icons in the place of letters in this same display. And it does work. People are able to make selections that way. It's just there's been pretty limited research on other language representation methods besides text in BCI, and any work that I'm aware of that's used icons, it's been a very limited vocabulary set. So nobody's really developed an interface that allows someone to have a lot of flexibility in constructing messages with icons yet.
Thank you.
All right, yeah, thanks for the questions. Keep them coming. This is just a demonstration of another type of BCI typing system that uses the P300. We don't use this one in our group, but it is probably the most common interface that's used in BCI research. It was this type of interface that's used in one of the only commercially available BCI systems that has appeared so far. So here the person is looking for the letter R, which is the next letter in the word free. And so they would just be focusing their attention on the R on the screen. And the R is going to be flashed as part of either a row or column. And every time it flashes, the person should have that P300 response. So the computer is going to do a series of row column flashes, and with each flash, it's gathering information about, okay, I didn't get a response on this row or column. Oh, I did get a response there. And it's kind of accumulating evidence to know that the person wants the R. So just another example of a different type of interface that uses the same brain signal. We're going to move on to a different brain signal called the steady state visual evoked potential, or SSVEP, which is a response to a flashing or oscillating visual stimulus. So think like a strobe light, something that's repeating at a constant rate that's really bright. It's measured over the visual cortex, and the frequency of the brain response is related to the frequency of stimulus presentation. So if we think about a light that's flashing at 4 times per second, like in the top row, or 6 times per second, or 8 times per second, so those different rates of flashing will produce a different response pattern in the visual cortex. Think about it like clapping along to the beat of a song. For a slower song, you're going to clap more slowly. For a faster song, you're going to clap more quickly. It's kind of the same thing. Your brain kind of tunes into the rhythm of that flashing. And again, it's an involuntary response that is sort of in time with the flashing that you're looking at. So we can use that for typing by associating different flashing rates of different areas on the screen with letters or groups of letters. Our group has developed a typing system that uses this brain signal. We call it the ShuffleSpeller, and it can be used with other access methods in addition to SSVEP BCI, but we've done a few experiments using it with SSVEP. One nice thing about SSVEP is it is collected over the visual cortex at the back of the head, and you can get a pretty good signal with a small number of electrodes. So we chose to use 3. We've been able to do it with just 1 in the center back of the head. But the nice thing about that is we were able to use this little headband that just had holes to put the electrodes in. And there's 3 in the back, as you see here, and then 1 in the center of the forehead. These were wet electrodes, but at least it was only a small amount of gel in those 3 locations. You didn't have to wear the full cap. So that was kind of a nice benefit of this system. And I'm going to show you what it looks like. So you can see here there are 4 LEDs. We're now able to do this with just flashing stimuli on the monitor itself instead of having the flashing LEDs. But each of those LEDs is going to be flashing at a different rate. And there are going to be boxes on the screen that the person will be able to select by looking at that flash. So we'll start our video here. We start with the letters in the center of the screen, and they change color to show what box they're going to go to. So we want the A, which now is in the orange box. If we were looking at the light next to the orange box, the computer knows that we wanted that box, and it's going to shuffle the letters again to get more information. So this is why it's called ShuffleSpeller. Once it knows what group of letters you want, it's going to need more information to know which of those letters. So it's going to reshuffle and kind of ask the question in a different way with different groups of letters. So we can I'll just let it follow along for a couple more letters here. So there the P was selected, even though it was in a box with a whole bunch of other letters. We already had pretty strong evidence from the first question that it wanted the P, so the yellow box was just confirmation. Here the language model is predicting that maybe the A or the L is pretty likely after APP. It knows the X is very unlikely, so it was able to choose the L. Again, it's predicting E or I as likely letters. This was a purposeful error for a demonstration video. And now it's going to select backspace, which is that little less than symbol on the left. Needs to differentiate between the N and the backspace, so it moves those to different boxes, and we're able to make a selection. So that's our ShuffleSpeller. Again, there are different types of visual interfaces that use that SSVEP signal, but this is kind of an example of how we are able to know what the person is looking at on the screen. And so you might think, well, why wouldn't you just use eye gaze if it can tell what the person is looking at? And that's a great question. There is some evidence that people are able to do this through covert attention. So if they don't have the ocular motility to actually direct their gaze at those different lights on the screen, they can still focus their attention on one light over the other lights. And that can produce enough of an SSVEP response difference for the computer to pick up on. So we're hoping this may be useful to folks with reduced ocular motility who have difficulty using eye tracking. We did test it with a couple of people with ALS who were unable to use eye tracking for a variety of reasons. You know, they had ptosis, so often their pupils were obscured by the eyelids and the tracker couldn't see them well. Or they did have, one of our participants did have reduced ocular motility and was not able to reliably direct his gaze to different parts of the screen. And both of the folks we tested with were able to use this BCI. So obviously we need to do more experiments, bring in more people. We are working on a new version of this with kind of some new improved features, but that's the basic idea of how it works and who we're hoping might benefit from it. I'll just talk about one more signal for non-invasive BCIs, and then I might pause again for questions. So motor imagery involves imagined movement, as the name implies. So you might imagine doing two different things. So imagine squeezing your left hand and wiggling the toes on your right foot. And that can produce different patterns of activity, primarily in the motor cortex, but as you can see kind of on this map here, it can be in larger areas of the head. This is maps of my own brain when I was imagining doing two different things. Of course, I now can't remember what those two different things were, but you can see it's a pretty different picture. So when we're monitoring EEG, again, the computer has been trained. It's given a bunch of examples of the user squeezing their hand and a bunch of examples of the user wiggling their toes, and it gets an idea of the pattern of brain activation that's associated with each of those imagined movements. And once we have those imagined movements established, we can associate them with different meanings. So for example, you might imagine squeezing your hand for yes and wiggling your toes for no, and have an application that could produce that yes and no response. Or there are motor imagery based systems that would associate one movement with advancing kind of a scanning interface, so advancing to the next item on the screen, and then the other movement with a click or selection. So we don't do motor imagery in our lab, but this is just an example of another fairly common signal that's used in non-invasive BCI. All right, any questions before we move on? Okay. Oh, is there something, Carolyn?
Yes, so Dr. Peters, you've shown a couple of different interfaces that you're using in your lab, and you talked about the characteristics of who might use the second one. Is that part of what you were doing, is building kind of profiles for users that might benefit from different types of interfaces?
That is something that we're doing actually right now. That's kind of the focus of part of the focus of our current grant. There is some evidence in the literature that different systems work for different people. You know, there are people who really aren't able to do anything with a P300 based BCI, but they can use an SSVEP based BCI pretty well. We don't have a whole lot. Excuse you. Oh, goodness. I'm sorry. Let me kick him out of the room and I will be right back. My apologies. Come here. No. You're being very rude. I am so sorry. He is usually quiet as a field mouse and just lays there quietly for the entire morning. And of course, this morning he decided he needs to be up and about and barking at squirrels through the glass door. So I'm sorry. So yes, we don't have a lot of information yet about why different systems work well for different people. There was a group that did a fairly large study using the matrix speller here, and they were kind of able to divide the participants into people who did pretty well and people who didn't do very well using the system. And they kind of looked at some of the covariates and what might explain the difference between those two groups. And the only thing they were able to come up with was the people in the not so great performance group, many of them did have some kind of visual impairment. So that's part of the reasoning behind our interface that is looking at letters in the center of the screen for folks who may not be able to really attend well to different areas of the screen if they're looking at different places in the matrix. So we wanted to keep it all in the center. So yeah, that is part of the goal, is to try to, you know, have a variety of options to choose from and to try to figure out who might do well with what. Obviously, there's going to be some trial and error, and you can't say everyone who meets this profile is going to do well with this system, but we're trying to come up with some guidelines and kind of give a starting point for what might work well.
Absolutely. We did have some questions come in as you were just speaking. The first one was, which interface so far would you consider the most effective or accurate?
For me, it's this ShuffleSpeller. I find it to be more accurate than the P300 speller for me. I also think it's more visually interesting. You know, it's like, ooh, just flashy, shiny things. I like the different colors. I like the animation. It kind of is just a little more visually interesting to look at than the letters flashing in the center of the screen. The flashing LEDs could be a little bit irritating to the eyes after a while, and we think that's going to be better with the new version where we're doing the flashes on the monitor itself instead of having the very bright external LEDs. So for me, it would be probably the SSVP ShuffleSpeller. But really, all of these systems I've shown can work very well for the right user, but they don't work well for everybody. That's unfortunately one of the major problems in BCI research right now, is they don't work well for everybody, and they seem to be less likely to work well for the folks who really need them. We need to figure out why. We need to come up with more options to work for more people.
Wonderful. Another question was, are you finding particular screen sizes work best with these interfaces?
Yeah, that's a good question. We haven't done a lot of investigation with different screen sizes. Let's see, I think this one in the picture here is like a 20-inch diagonal screen, and we've used something around that size for most of our studies, especially with the RSVP keyboard with the letters in the center. You can imagine using a much smaller display for that, because really the only screen real estate you're using is kind of that point right in the center, and then a little area for the message window to show the type string. For SSVEP, you probably want a larger monitor so that those flashing lights can be a little bit further apart. If that just makes it a little bit more clear, it makes the SSVEP response be a little bit more clear about what frequency it's associated with if they're a little bit further apart. But there are kind of some alternatives to SSVEP that use a similar signal where you can have targets closer together. So it's just evolving all the time. And I think that we will have BCIs that can work with smaller screens. In fact, there are companies that are looking at doing it on augmented reality goggles. So having an interface actually projected on the goggles, which is pretty small. So yeah, we're using bigger screens, but there will be options.
Thank you. And you also had an empathetic statement from another dog lover who understood your plight.
Thank you. I appreciate your understanding. He's a great little guy. He's just making my life difficult this morning. It is morning still over here on the West Coast. Okay. Well, let's move on and talk about implantable AAC BCIs. So these are systems that do involve some sort of surgery to actually place electrodes inside the body, on or within the brain. There are a few different ways of acquiring these signals. One is electrocorticography. This is sometimes referred to as partially invasive BCI. And that's because it involves an electrode grid that sits on the surface of the brain. So it's partially invasive because they do have to do a craniotomy. You know, you have to expose the surface of the brain, but then the electrodes just kind of sit there. They're not within the brain. This is something that is often used for people who are having monitoring for epilepsy to try to localize where the seizures are happening. That's a kind of a major use for it. And so some implantable BCI research involves participants with epilepsy who may not be potential BCI users, but because they may be sitting in a hospital for a week with already having electrodes on their brain, they may be asked, hey, do you want to participate in a study as long as you're here? Do you want to try controlling a computer with your brain? So that's where some of, especially the early implantable BCI research was happening. Other types are microelectrode arrays and endovascular electrode arrays, and I'm going to show you an example of what each of those looks like. Those are the more fully invasive, I guess, types of electrodes. So BrainGate is a very long-standing BCI research group. BrainGate is the name of their system, and they have implanted these electrodes in a few different people now. And you can see the electrode array in the top right. So the size of it is this little square on the penny on the left. So it's really blown up in the image on the top right. And you can see it's this little plate with a bunch of spikes coming out of it. And those spikes actually do protrude into the brain and make contact with neurons. You can see the placement of the electrode array in this person in the lower left image. Kind of placed in a motor region of the brain. And then you can see the actual person here on the right. There is an arrow pointing to his head. Let's zoom in on that. It is pointing to a little box that's sitting on top of his head. So this is a wired system. The wires come out of his brain through his skull to what they call the pedestal, which is actually kind of a little plug that protrudes through the skin and is sitting there on top of his head. And then they can, attach this little box to it, and that's how it actually connects to the computer. So this, involves surgery, and you do end up with kind of a little plug sticking out of your head that is, there are some risks associated with this. So this is what one type of implantable BCI looks like. This is the other type, the endovascular electrode array. The Stentrode is the brand name of, I think so far this is the only device that works like this. But the idea is that the surgery required is less invasive because this electrode array is inserted into a blood vessel. So they can actually start somewhere else in the blood vessel and kind of get it up there in the brain without having to do a craniotomy and open things up. Let's zoom in a little bit here. So the electrode kind of looks like that sort of mesh tube that just fits into the blood vessel. It expands against the walls of the blood vessel and makes contact with parts of the motor cortex. And then that is connected again with wires that go down through the blood vessel, down to the chest area where there's a little piece of equipment that sits under the skin. And then this time there's nothing that protrudes through the skin. You would attach this external piece on the other side of the skin. So it's kind of like a cochlear implant where there's a piece that sits under the skin, and then there's an external piece, and the signals are transmitted through the skin. So then that is connected to the computer. There's also an arrow pointing to the eye tracker here at the base of the computer. So far, as far as I'm aware, the way that they're using this BCI is only for clicking. So they have an eye tracker that people use for cursor control and for zoom, and then they're clicking with brain activity. This is a little bit newer technology than BrainGate, so I don't think they have a full BCI only typing system yet. This was developed in Australia, but I believe they're now undergoing, trying to get FDA approved here in the US, so we may start seeing some clinical trials with the Stentrode here in the US. And now I want to show you some videos. So our research group does not do invasive BCI. So I'm showing videos from other labs. I just want you to get an idea of how these systems work. So let's do another screen share. Here it is. Okay. Is that what I want? Yes. Okay. We'll make it full screen. So this is a woman who is using BrainGate. You can see the little pedestal on her head up there in the top left. And she's using kind of a point and click type system. So pretty similar to cursor control on a typical SGD. She's just doing it with her brain. And let's see what that looks like. So this is real time. She's had a lot of practice, so she's pretty skilled with controlling the cursor here. And they've asked the participants in this study, you know, how do you do it? How do you control the cursor? And the response, as far as I've heard it, is pretty much, I just do it. I just do it. I just think about it, and it sort of happens. Through trial and error, they kind of learn to control the brain activity around that electrode. So this is her free typing, pretty quick. The line at the bottom is showing the correct characters per minute, which gets as high as 40 correct characters per minute. So pretty quick, much faster than most of the non-invasive BCI systems, which are more on the order of 5 to 20 characters per minute. Okay. I'm going to show you another video using the same BrainGate hardware. So the same pedestal and little box on top of the head. In this one, instead of having control of a cursor and a click, this person is using imagined handwriting. So he's actually imagining moving his hand to write letters on a piece of paper. He's imagining holding a pen and moving that pen across a piece of paper. And they were able to differentiate what the brain activity looked like when he was imagining different letters. So let's watch a video. So we see there again that electrode array. This person has 2 pedestals. He had 2 electrode arrays implanted and 2 ports coming out of his head. That's a more recent version of the BrainGate hardware. So again, it's not as simple as him just thinking these words or thinking about the letters. He is consciously, very intentionally imagining the movements of his hand to form the letters. The top left video here is basically a different keyboard layout of the same thing that the woman in the previous video was doing with that point and click. And then this is the new version with the imagined handwriting. And as they point out, it is faster. All right. So my dog's in here making noises again. Hopefully you can't hear that too much. I'm going to show one more invasive BCI video. This is a different research lab. This is Edward Chang's lab, and they use ECOG. So you can see if I can make this bigger.
UCSF researchers have shown that full words and sentences can be decoded from the brain activity of a person with paralysis who is unable to speak. Dr. Edward Chang's team worked with a brainstem stroke survivor who lost the ability to articulate words 15 years ago. The man has relied on other limited means to communicate. In this study, an electrode device was implanted over the brain.
All right, so here's what I'm talking about, ECOG. So instead of the little electrode array with the spikes in the BrainGate system, this is kind of a plate, a grid of electrodes that's sitting on the surface of the brain. So this is that so-called partially invasive BCI setup.
Area that normally controls the vocal tract. A question was displayed for the participant, and the device recorded brain activity while he attempted to speak and reply. A computer algorithm translated the brain activity patterns into words and sentences in real time. The computer algorithm was trained to differentiate among 50 words that could generate over
I think the sound may have cut out.
Okay. Reshare my slides again. All right, so again, with that last one, it's not like he's just thinking the words and they appear. He is very consciously and intentionally attempting to speak those words. So he does not have the muscle control. He's not physically capable of speaking, but he can still attempt as if he's trying to speak those words. So he is imagining moving his articulators and how he would produce those words. So very, very intentional. And hopefully you caught it in the video, but this was done with a closed vocabulary. So there were 50 words that the computer was trained to recognize what this person's brain patterns looked like when he thought those 50 words. So this research is still pretty young. It's not able to just, write anything that the person can imagine speaking, but that is what they're trying for. And there is some more recent research from this group where they're getting closer to being able to do things kind of on the phoneme level to allow more flexibility and a full vocabulary. All right, any questions about any of these invasive hardware or typing systems?
Yes, so Dr. Peters, at this time, the invasive systems are only being used with people who had pre-existing motor plans for speech or writing, correct? They are not been tried to people who didn't have speech or literacy skills preceding this event.
I am not aware of any BCI systems that have been implanted into people with congenital impairments. Yeah, it's so far, the only ones I'm aware of are people with acquired disabilities who had previous movement experience and good literacy skills.
Okay, thank you. And then we have a question in the chat. Are you seeing any other evidence fatigue factors from an access perspective that occur with any of these interfaces?
Yeah. Mm-hmm. Yeah, I can't speak for the invasive systems. We definitely notice a decrease in performance with fatigue. We've done a couple of studies where people are asked to do a fairly long session, and we are specifically interested in looking at the change in their performance over time. Fatigue does seem to affect people's ability to use this system. There have been a few studies where people have been left with the BCI system in their homes. They've been provided with training for the caregivers, remote technical support. and then they're kind of monitored and of how they're using the system. And there were definitely folks who were able to use the BCI for several hours a day and used it for communication, used it to type. There are some brain painting applications that people have used independently in the home. So it is possible to use it for several hours, but for various reasons, both the attention demands as well as potentially, staring at a screen for hours, it can be fatiguing.
Thank you. The next question is, all this looks amazing. Are there any of these interfaces, non-invasive or invasive, that are commercially available?
Yes, that is definitely going to be part of the practical issues section in a couple minutes here. Unfortunately, no, pretty much everything is in research or beta testing at this point. The invasive implantable systems especially are only being done as part of research studies. It's possible to kind of DIY assemble a non-invasive system. I mean, you can buy EEG equipment, you can get open source software for typing, but there's nothing you can just buy and that's usable out of the box. There's no technical support available, pretty much. Really, it's just research at this point, unfortunately.
And Dr. Peters, I know this is a question I get very commonly in teaching about this. Do you have any sense of how long it might be before something like that were to reach the market?
I feel like we've been saying in about 5 to 10 years for like 20 years now. It's getting closer. I mean, the field is making huge strides, but it's really tough to say. I'm still hopeful in the next 5 to 10 years, or hopefully sooner, but it's so hard to say.
Absolutely, thank you.
Okay. So now just quickly about potential BCI users. Traditionally, the target users of BCI systems, it's been considered to be people with locked-in syndrome. Locked-in syndrome is most often associated with severe stroke, particularly brainstem stroke. It can also be caused by progressive diseases like ALS. If someone with ALS elects to get a tracheostomy and go on mechanical ventilation to prolong their life, their voluntary motor function will continue to deteriorate and they may be left in a locked-in state. There are a few different versions of locked-in syndrome. There's total LIS, where a person has no voluntary movement at all. Classic LIS, where they have some eye movement and maybe blinking. And incomplete LIS, where they have very minimal voluntary movement, but they have some other reliable body movement. So that might be twitching a cheek or an eyebrow, or maybe they can move a finger a little bit. So something else that they can do where they might be able to activate a switch or give a signal to a communication partner. So really it's folks who are not well served by existing access methods, either because they have total LIS and they have no movement at all to use with a traditional access method, or perhaps, maybe they have some eye movement, but it's not enough to control an eye tracker, or maybe they can even activate a switch, but they're not able to do that reliably. Maybe that works just fine for them in the morning, but after using it for an hour or two, they're too fatigued to continue using the switch, and they're not able to use movement for access. So this is where BCI comes in, is to kind of fill in those gaps and provide an option for folks who don't have good options right now. And for implantable systems, of course, any target user of an implantable BCI would need to be a good candidate for surgery. The potential benefits would need to outweigh the risks. So that's now. In the future, we don't really know who target BCI users are. There are, as I mentioned, companies that are looking at BCI applications for the general population. Companies like Neuralink, for example. Facebook had a BCI division for a while, although I believe they're not doing that anymore. But Facebook's original idea was everyone should have a BCI and they could interact with Facebook through their BCI. This was slightly terrifying to me, but also I thought, okay, great. They're going to put their money and brain power behind developing this product. And if they see a market for it, they're going to make it work really well, and they're going to bring down the price point and make it more available to people with disabilities. So in the future, we may see more people using BCI. And as the systems become better, you know, if we have faster, easier to use, more reliable BCIs, if the surgery becomes easier and more available, it may get to a point where even people who have an existing access method might choose to use BCI. It may get to a point where it works better than what's out there right now. Right now, I would say BCI is an access method of last resort, but that may change as the technology develops. Our group did a systematic review of research involving AAC BCI systems used by people with disabilities. The most common diagnosis represented among those study participants was ALS. About 70% of the studies we found included participants with ALS. About 20% included people who were recovering from stroke, spinal cord injury, muscular dystrophy. A few studies involved people with cerebral palsy, and some other conditions you see there. Everything I've talked about so far and the work that our lab does involves adult BCI users. There's pretty limited research on BCI systems for children, but I just wanted to bring that up. I think there may be some folks here who are interested in that. Pretty limited research, but they have looked at kids using BCI for typing, for icon selection, for games, and for visual art. If you're interested in BCI for kids, I definitely recommend checking out the BCI CAN network, which is composed of a few different hospitals and universities in Canada that have pediatric BCI research programs. They're at BCI for Kids on Twitter. You can check them out and see actually some artwork that was made by kids using their brain activity. They hook it up to one of those Sphero balls that you can control the movement of, and they coat that ball with paint and have the kids roll it around with their brain activity to create these really beautiful paintings. So there is work on BCI for kids, but it is very, very early days yet. All right, and finally, I want to go through some of the practical issues, potential obstacles for BCI as an AAC access method. As we were talking about a couple minutes ago, really the availability is kind of the main factor right now. But there are issues related to performance, adaptability to user characteristics, noise and artifacts, discomfort, the risks of implantable BCI, and caregiver burden. Talk a little bit about some of those. So really, there are few, if any, options for BCI for home use. There used to be a system called Intendix that was being sold commercially. It looks like the company is not selling that anymore. And I did a pretty extensive Google search trying to find if anybody was selling a spelling BCI, and nothing. Everything that I found was intended for research. BCI hardware prices, you can get lower end EEG equipment for about $500. The higher end stuff goes up to the tens of thousands of dollars. You can get open source software if you wanted to DIY a BCI system, or if you know one of your clients who has a very tech savvy friend or family member with lots of time on their hands and might want to set that up, it would be possible, but there's really no support available. Insurance coverage has not even really been addressed yet because these systems aren't very available. I've heard of a few cases of veterans who were able to get funding through the VA for this system that used to be available as kind of an out-of-the-box BCI, but I have not heard of anyone else getting funding for a BCI through any other insurance provider. Performance is still an issue. The BCI performance of people with disabilities is pretty poorly described in the literature. We found in our systematic review that some studies would say, oh, great, we had 95% average accuracy, but they also said, well, we excluded about half of the potential participants because they didn't reach an initial performance criterion. And then there are other studies that don't talk about whether or not they excluded people with an initial performance criterion. So it's hard to know whether the reported results actually represent good performance. It's hard to know how many people with disabilities these systems actually work for. but the literature does show high error rates for some users with disabilities. You know, some people are able to use these systems with 100% accuracy. Some people are 0% accuracy and really can't use it at all. Typing rates are pretty slow, especially for the non-invasive systems. And as I mentioned earlier, we have found that different systems work better for different users. So that's kind of the hope for us is, you know, just because somebody tries BCI and it doesn't work, that doesn't mean BCI doesn't work for them. It means that particular BCI doesn't work for them. And once we do have options available, we're going to be able to try different systems and see what works for an individual user. Adaptability to user characteristics. Again, BCI performance can be affected by fatigue, attention, medications. A lot of the medications that many people with disabilities may take every day can affect either EEG activity or attention and fatigue. We also need to think about the sensory skills needed for user interfaces. So people with vision impairments or ocular motility impairments, how can we design or adjust a visual interface to help them use it? Or maybe they need an auditory only interface. And we just need systems that can be customized to suit user preferences. Beyond making it work, we need to make it work the way that people want it to and look the way that people want it to, make it comfortable to use. Noise and artifacts are big issues with BCI systems. These are things, again, that can, noise that can obscure the BCI control signal. This can be caused by things like muscle activity, eye movements or blinking, spasticity, for example, in people with cerebral palsy. Can also be caused by electrical interference from other equipment in the room, things like ventilators, things that are present in the rooms of, again, many people with disabilities. The hardware is typically designed in such a way to try to alleviate the electrical interference, but it can still be an issue. And then just things like loose or worn electrodes can also cause noise and artifacts. Discomfort can be an issue, again, headache, eye strain, skin irritation or breakdown from the electrodes for a non-invasive system, gel in the hair if you're using wet electrodes. The risks of implantable BCIs, of course, any surgery or anesthesia experience is risky, even for people without disabilities. There's a risk of inflammation around the electrodes, or over time scar tissue can develop, and that actually reduces the effectiveness of the electrodes. These systems are pretty new. We don't really know a whole lot about how durable this hardware is. Is there going to be a need for another surgery to replace some of the hardware? There's a risk of skin erosion or abnormal bone growth around the pedestal in the wired systems. And finally, caregiver burden. These systems, the non-invasive systems, require, placing the electrode cap, adjusting it so all the electrodes are in the right place, making sure that the electrodes have a good connection and that the signals are of good quality. You have to know something about EEG, maybe someday the software will be set up to try to make it really user-friendly. Maybe there'll be alerts that will tell you exactly what you need to do to adjust it and fix it. But right now there's a pretty steep learning curve to being able to set up these systems. Caregivers would have to troubleshoot when things go wrong, clean and maintain the hardware. It's kind of a lot with the way these systems are now, but again, we're hoping and expecting that will improve with further development. Okay, does anyone have more questions before we talk about a case study?
Yes, you went through a lot of different factors and considerations that have to be taken into account when assessing somebody for these types of systems. I'm curious, with the large team that you work with, and you mentioned many different types of professionals, what type of teaming are you envisioning when this does become available being required for a successful assessment? Yeah,
that's a really good question. And a lot of this is hypothetical right now. I think eventually, hopefully it will be similar to kind of existing SGDs. Hopefully they will be set up in such a way that clinicians or family members can learn how to program and customize them. We will need, of course, specialized training for SLPs and others who may be involved in this. especially for implantable systems, it's going to be an interdisciplinary thing. There's going to be discussions with neurosurgery, neurology. Yeah, it's definitely going to take an interdisciplinary group. And I think that's something that we'll figure out as these systems become clinically available.
Thank you.
Okay. Did anybody, I have a case study that I kind of made up, but is there anybody who has kind of had a case study come to mind as we were talking through this? Is there anybody that came to mind that you're wondering about how you might think about BCI for this person?
Nothing in the chat yet.
Okay. All right. So we'll go through our hypothetical friend Leo here. So Leo is a 65-year-old male veteran with ALS. He attends multidisciplinary ALS clinic at the VA. He is anarthric. He has minimal movement of his upper and lower extremities. So we would probably consider him to have incomplete locked-in syndrome. You know, he still has eye movement. He has some small other movements elsewhere in his body. He has undergone tracheostomy and receives mechanical ventilation. And his goal is to prolong his life as long as possible. He wants to, you know, see his grandkids graduate from high school. He wants to participate in family events. He wants to stick around. And he's currently using an SGD with eye control, as well as partner assisted scanning and eye movement or gestures for yes, no. You know, he can do a subtle thumbs up with a little move of his hand. He uses his SGD for face-to-face communication and video calls, for emails to friends and family, for environmental control, and for other purposes. And so he's noticed that his ability to use the eye control with his SGD is changing. It's not always as accurate as it used to be. Sometimes he has ptosis and the tracker has trouble seeing him as he gets tired. He knows that this is going to continue to change, that he's going to continue to lose his voluntary motor function. And he's seen news stories about BCI and is wondering if it might work for him. And so again, you know, BCI is not really ready for prime time yet. It's not really out there. So this is all kind of hypothetical. You know, if a couple years in the future, we met Leo and he was asking about BCI, how might we deal with that? So the way that I would think about it is kind of feature matching, just like any SGD. It might start with those broad categories of non-invasive versus implantable, talking about the pros and cons of each of those options. It might be starting with non-invasive and trying a couple different systems to see if there's something that works really well for him. Of course, discussing the surgery risks with Leo and with a multidisciplinary team, including neurosurgery. Thinking about the user interface, so different keyboard layouts, rate enhancement features, thinking about whether it can do the things that Leo wants to do with his computer, email, environmental control, thinking about different signal types. And again, hopefully in the future, we may have some guidance about, you know, which signal type might be best to start with for Leo, but it would be worth trying a few different things and seeing what works for him. Thinking about the ease of use of the system with the physical setup of the cap, if there's a cap involved, with operating the software, and how that works with the support that he has available. I think we would be careful to provide information and manage expectations. You know, again, making sure that Leo and his family understand that it's not a mind reading device. I think it might help in cases like this, where someone has previous AAC experience to relate BCI communication applications to their current methods, to kind of emphasize that it's really an access method more than a thought to speech translation device. So SSVP is kind of similar to eye tracking. It's a way of knowing what physical area of the screen the person is looking at or attending to, except instead of tracking the movement of the pupil, we're able to tell what area of the screen he's looking at by looking at those flashing lights, what area of the screen is flashing at the rate that his brain is responding to. Partner-assisted scanning, you could think about as analogous to P300. So with partner-assisted scanning, there's a partner who is presenting groups of letters or letters and looking for that signal of, yes, I want the M group and I want the letter O. Similar thing with P300. The computer is presenting options, and with your brain, you're able to say, oh, yes, that's the letter I want. Gestures and blinks for yes and no. I didn't fill this in, but that would be analogous to motor imagery, where just instead of a physical gesture, a thumbs up or thumbs down, or looking left or right, you're imagining two different gestures, an imagined gesture instead of a physical gesture. And of course, for non-invasive BCI, we would want to conduct device trials, just like we would in any AAC evaluation. Hopefully arrange a trial period for home use so Leo and his family can see how BCI fits into their daily life, what the actual setup is like, whether it's possible to use it well without constant support. And of course, assessing both the performance and Leo's user experience, how he perceives using it and how easy it is for him to use. So again, these are just sort of some hypothetical things that I've been thinking about how I would approach clinical implementation of BCI, but it's really kind of an open question right now. We'll try to apply the things that we know from existing AAC access methods, but there are definitely going to be some unique issues that come up specific to BCI. I think that's all I have. Yeah, so are there any other questions? Thinking about a case study, are there any other questions that you might want to ask Leo, or other information you'd like to get about him when thinking about BCI, or other information that you think you would provide to him and his family? I know it's kind of strange to think in hypotheticals like this, but. Okay.
Yeah. I'm sorry. I have a question, Dr. Peters. It's something that Carolyn and I were discussing offline. Is there, and I apologize if you've covered this in your talk and I missed it, but is there a contraindication for individuals who are experiencing any kind of seizure activity?
Yes, specifically for photosensitive seizures. So epilepsy that is not triggered by flashing lights, there's no problem with that. But yeah, it would be a contraindication, particularly for the SSVEP or anything where there's flashing involved. That would not be a good fit, but they might be able to do something like the motor imagery, where it's more of a self-generated brain activity rather than a response to something flashing on the screen.
Thank you.
Good question. Other questions?
We did have a comment pop up in the chat from Rhonda, who said she would be interested in knowing his personal preference for a system. Yeah, absolutely. Yeah, so again, his preference for whether he's interested in enduring the risks of surgery after having a conversation with his providers, his preference for how he would use the system in everyday life, his preference for what he needs it to do, whether he needs to have word prediction or finds word prediction annoying and just would rather it not be there. Absolutely, we need to consider his preferences. Okay.
All right, thank you. If I can very quickly, I'm going to take back the screen. All right, we want to thank everybody for attending our final session in this ECHO series. We do have a post-session survey that we will drop in the chat. We would love your feedback on session and information presented as a part of this series. So we appreciate your involvement in that. It is optional. We do have the website and everything listed. You will see at this time, there are no further sessions that are currently scheduled. But when we do have further events, we will post all of those. There is a CEU participant form. We will send it out after the session. We're also going to drop it in the chat for you here today. Feel free to email that to the team. We will be collecting these through December. You only need to fill it out once for the whole series as we're tracking attendance, but if you haven't filled one yet, please fill that out and send it back. And then here are the contacts for myself, Dr. Firestein and Dr. Peters. If there's any questions about anything that you saw that didn't get discussed today, please feel free to reach out. And again, we appreciate everybody's participation in the series. Hope everyone had a happy holiday, and glad to have you back. And please don't hesitate to reach out. Bye, everybody.
Thank you everyone for coming today and for asking great questions. Hope I answered some of your questions about BCI, and we'll see what happens in the next few years. Thanks, everybody.